Okay, so welcome to class again. So we're gonna continue on the last topic, a special seminar on two-photon polymerization. Some of them are actually, a lot of them were research output from our groups to parallelize two-photon polymerization process. As I explained in the last lecture in the past, two-photon polymerization is performed by raster scanning the focal point. And it is usually a sequential process and very, very slow. So our goal is to, parallelize the process. There are two ways. One way is to generate multiple laser foci. Well, if we can generate 100 foci, then the throughput is going to be increased by 100 times. If we, on the other hand, can generate a light sheet, containing tens of thousands or hundreds of thousands of points, then fabrication rate can be further improved. So let's start with generating multiple laser foci. So there are multiple ways to generate fixed laser foci. You can use, for example, diffractive optical elements or micro lens arrays. But when you do that, individual focus cannot be controlled. So you can only use the generated foci to fabricate periodic structures. So application is sort of limited. And on the other hand, if you use micro lens array, usually the point spread function or the quality of the focus is compromised. So we want to obtain high flexibility, for example, to generate multiple foci, but individual focus can be controlled at high speed. And I remember from the last lecture, we talked about the use of digital micromirror device because it has so many different pixels and the speed is on the scale of 30 kilohertz. Okay, I remember we talked about using the digital micromirror device as a binary mask because each pixel has only two states. It's plus minus 12 degrees. As a result, one can use it as a programmable binary mask. And when you encode wavefront information in a hologram, in a sense, this is a binary hologram, display on the DMD, you can recreate the stored or designed wavefront by bringing a reference beam to the hologram. As a result, the stored information is going to be recreated, okay? And this pattern here shows a binary mask. As you can see, it only has black and white, two colors. So how do you store information in holograms? Well, so in analog or film holograms, you just expose light and it's sort of stored in an analog way, just like films. But digital holograms are designed differently. But fortunately, these principles have been derived in the 70s by Lee. So a lot of times we call these Lee holography. There are other different binary algorithms available, but this is a good example. So whichever wavefront that you want to encode in the binary hologram, you just basically substitute the wavefront information in the inequality. So if it satisfies this inequality, then you assign the value of 1 and otherwise 0. So based on this formula, you can calculate the binary mask on the DMD. So I and J here represents the coordinates on the DMD. So you can see the different beam modes, airy beam, bezel beam, LG beam, with the governing equations, and substituting these equations into the inequality, you can have the binary mask design on the right. Okay, so that's airy beam, bezel beam, an LG or donut beam, or an arbitrarily designed wavefront, which is a P-stove here. So on the left shows the measured intensity profile. So this shows that you can encode any information in the DMD in the form of a binary hologram. Okay. So this is the first example. We demonstrate how to use this hologram to perform fast scanning. So essentially, since holograms can store any wavefront, so we just use a spherical wavefront. So when a plane wave becomes a spherical wavefront, it's going to focus, just like this one here. So these are plane, but after they see the DMD, they become a spherical wavefront and have a focal point. So you design multiple holograms and each have a different radius. Then you're essentially scanning the focal point along the axis as shown in this figure here. And this is the phase information of spherical wavefront. So by following the same formula, we convert that into 0 and 1s. Okay, so you can see from here, this is the DMD beam shaper. Okay, as I explained last time, most of the optics here are designed to compensate the angular dispersion introduced by the DMD because ultra-fast lasers are very sensitive to dispersion. So if you don't compensate them, it's going to widen the femtosecond laser pulses and lowering the peak power such that they cannot induce multi-photon polymerization or absorption. So this is, we put the DMD scanner in this 2-photon microscope. So you can see this is a video array system. This is a high-speed polygonal scanner. And the secondary scanner is a Galvo mirror. So to scan or visualize things at video rate, the Galvo mirror is going to scan at 30 Hertz. Okay, 30 frames per second. And this is much faster. Okay, so at each point, the emission is collected by a photomultiplier tube. And collecting these points, we can use a frame grabber to map out a 3D image. Okay. We also mentioned we have derived a parametric relationship to relate the distance we can scan using the DMD, as well as the minimum step size. We can command a focal point to its neighboring point. So in this equation, n refers to the refractive index. F is one of the focal distance going to the objective lens. But most importantly, there is the objective lens magnification. And also here, actually we should look at this equation. So in the denominator, there's the square of magnification. There's the number of pixels in one direction. So we know that the lower the magnification, the larger the scanning distance. And the more the pixels, or n times d, this equals to aperture. Okay, so actually a smaller aperture will give further scanning distance. But looking at minimum step size, we find that it's also having a functional relationship between the aperture and magnification. And obviously, the more pixel and the higher the magnification will give us a finer step size. So to visualize or intuitively understand this, we just use a 40x objective lens into the system, and we find that based on the equation, we can have a scan range around 500 microns and the step size around 270 nanometers. So this is fine enough because a point spread function or a voxel is roughly 2 microns in size. So that means we can divide this into 10 segments, and we can determine how each voxel would overlap. So that's fine enough resolution and also large enough distance. And these two charts shows the equation predicted relationship versus experimental measurements, which is quite accurate for both 40x and 60x magnification lens. Okay. So this is actually where we stopped last week. We show to use the DMD scanner to perform axial scanning. You can see that the resolution is very good, comparable with mechanical scanning. But in using the hologram, we don't really need to scan to a neighboring point. We can scan at any place in the DMD work volume in a non-continuous fashion, because each hologram refers to a specific location. So if we just jump between these 2 points, we don't really need to go through the space in between. Okay. So what we've shown is we use the phase term to control the axial position. So phase, psi here is just spherical wavefront. The second term here, R over T, is typically in a binary hologram called the tilted phase term. So basically, if we control this term, we can laterally move the focal points. And it would not be surprised that if we can, control the axial position, we can certainly control the lateral position by using the same method. Okay. So the tilted phase term is equivalent to the spatial frequency on the DMD or the fringe pattern. So you can see here, if we vary the fringe patterns here, we can, move the lateral position accordingly. It has a perfect linear relationship from the spatial frequency versus the lateral displacement. And this shows the diffraction order movement. So this is actually the diffraction order that we're controlling. And all the encoded hologram information is represented in this first minus order. Or, you can also use the plus order. The 0 order has no phase information, so we need to block out, redundant diffraction orders and only use this one for application. Okay, so following the same procedure, we perform an experiment to figure out how far it will move in the lateral direction. And under a 40x objective lens, it will move around 200 microns and an even better step size, around 130 nanometers. So we all know that holograms can be superposed. So that's how we generate a 3D motion control of a focus. So we can design x-axis and combine it with y-axis and then superpose it with z-axis. So these holograms will accordingly, change according to these superposition. And shine the light to this hologram would automatically bring the focus to another design point in space through a discrete method. Another thing you can do is after you design one point, you can add another focus scanning information and just superpose them. So you can split the laser focus into as many as you want by superposing design holograms. So the video here actually shows 4 foci operating in parallel. And you can see they can be individually controlled at 22 kilohertz. So this is the first demonstration of this high-speed, high-flexibility control. These 4 foci have the same work volume. And you only see 2 written structure because the other 2 structures are out of focus, so you don't really see them. So this is basically writing in liquid photoresins. The other thing you can do with hologram is you can perform wavefront correction. So this is again done by superposing wavefront correction information into the hologram. So you can split laser foci. You can split a focus into many foci. You can, for each focus, you can also add a wavefront correction phase and to fine tune the spot size. And one issue I like to mention is, you know, if you manipulate the wavefront, you would, and to induce scanning or displacement of focus, you will find that as you move away from the focal plane, your point spread function or voxel size is going to degrade. And there's nothing you can do about it, as we discussed. Wavefront correction cannot, you know, correct the focus to sub-diffraction limit or correct inherent aberrations. But one thing you can do is you can worsen these nice and small spots into bigger ones, okay? So for fabrication, the key is really not how small the voxel is, but instead is how uniform each voxel is. As long as they are all uniform, then we can control the laser power, fine tune it, and to achieve super resolution by writing with precise power just above the polymerization threshold. And we will use this method in the later light sheet technique, as we will show briefly. Okay, so here is a brief comparison comparing with a conventional writing method. So all the commercial system use raster scanning. So let's say we're writing a 2D structure, like this is a home with 2 pillars. So conventional method, you would write one layer scanning point by point, and then you go to the second layer. When you see things you don't want to write, you close the shutters and then reopens it. Okay. But no matter what, you need to go through all the point in space, layer by layer. Okay. And using the DMD bin shaper, what we can do is we can generate multiple points. So each color here represents a single exposure. Okay. So what we do is we lay down the foundation. This is the first exposure. And the second exposure, we can create these pillars, but we don't really need to scan because we can convert the focus into a bezel bin. So bezel bin has a column geometry as shown here. So, you know, there's 6, 7, 8 different colors. That means, you know, in roughly 8 milliseconds, we can complete the fabrication. And more importantly, we don't really need to go to these empty spaces to expose, because each point here represents holograms, and we move to the next batch of points by switching to another hologram. So that's very effective. Okay. So we use DMD to demonstrate fast single point scanning first. And that practically retires all the mechanical scanning components in a laser scanning microscope. So you can see this is what we do first. So this is a femtosecond laser, and we put a DMD here and, you know, some static laser dispersion compensation components. So these are static optics. And then we just use DMD to scan the focus, you know, to write stuff or image stuff. So the emission then goes back and collected by the low light detector, which is a photomultiplier tube. So this is the simplest 2-photon microscope you can find. And DMD, of course, is a low-cost component. So this would be a scanless, high-speed 2-photon microscope in a way. Now, to perform fabrication, all we need to do is, you know, replace the PMT but with a regular CCD camera and a back illumination. We will be able to see the fabrication process. Actually, let's see if this will play. So here we can see parallel fabrication using 1, 2, 3, and 4 laser foci. And you can see the speed enhancement by a factor of 4. And you will notice that when you use more than one foci, the fabrication quality is slightly deteriorated. But if you look again, you find the resolution doesn't change. It's the uniformity is compromised. And this is due to the fact that if you split focus, the laser intensity is not going to be split uniformly. And these issues can be resolved by using some iterative algorithms to improve the laser uniformity split between or among different foci. Okay. And one question people often ask is how many foci you can use. And the answer is it's only limited by the laser power, because if you use 2 foci, that means laser power is going to be equally split. If you use 100 laser foci, then at each focal point, the power is 1/100. So as long as you have sufficient power to polymerize all points, you can generate and use as many foci as possible. And this fabrication of a checkerboard, this video here shows a unique feature that we can control the dose directly. So this is basically a scanning done quickly. Actually, let me use the pen. The scanning done quickly in one direction. So at each point, we switch to a different hologram. But each hologram contains a different position and amplitude information. So as we scan through, we can actually tune the laser power and alternating between 16 to 8 milliwatt. Okay. So they are of different height, but these are all written structures. And the total fabrication time here is about 1 second. Okay, so this slide shows more high resolution fabrication results using the DMD scanner. So you can see these structures are finely printed. You can also see some details here. These voxels are actually overlapping in space. So you can see some periodic structures on these fabricated beams. One issue people often run into is some deformation that you see on the beam. So under the microscope, they look perfect, but after development, they would deform. And this is mostly due to the surface tension in the liquid developing solution. As they dry, the surface tension often deform the structures. So this is very similar to the effect of stiction in MEMS fabrication. Remember, you have a freestanding structure. As you dry the resin or a cleaning solution, the liquid surface tension brought down the structure and sometimes damage it. So to resolve the issue, same solution can be used, CO2 supercritical drying system or a freeze dryer to remove the liquid through sublimation is a good way. Okay. So here is a quick summary of how things were done in our method. So you can create any structure using a commercial CAD software. Once you complete that, you store or save the file as in the STL format, which is a 3-dimensional point array. So we then convert each point into a hologram, and that's automatically done in MATLAB. Once you have the hologram, you load it to the DMD memory, and it's going to automatically sweep through the hologram on the DMD, and the focal point is then scanned accordingly. Okay, so after that, we develop the written structure and get the 3D parts done. So this is a illustration of a trajectory generation process and the actual scanning process. So actually, if you are familiar with 3D printing, one core research area is trajectory planning. And many macro scale 3D printers adopt, 5 or 6 axis writing head to print in different trajectories to optimize the mechanical strength or structural strength of the printed structure according to different optimization objectives. And in the DMD scanner, this can be done easily because whichever direction you want to change or print, you just alter the sequence of the binary hologram in the DMD memory. And the scanning path will change accordingly. Okay, and after development, this is the structure that you will see in an SEM. Okay. So we have fully automated the process and custom design everything to be integrated in a compact system as shown here. And this system is simultaneously serving as a 2-photon microscope. Okay, so this is a quick summary of the advantages of the DMD scanner. Has very high speed, 22.7 kilohertz using DLP 4100. It's a specific DMD model we choose. It generates multiple foci for parallel writing. And we can perform random access on each generated focus. And also each focus can be individually controlled in terms of both location and intensity, so that we can control the dose. Okay. We can also convert the Gaussian beam into various novel beams as we shown earlier and maneuver them in space. Okay. So this address one challenging problem to write overhanging structures. So meaning, if you have a structure like this, because 2-photon polymerization is essentially done in liquid solution. If you write one layer at a time, you find that when you're done with this layer, these two parts are actually disconnected. Okay. And once liquid is polymerized, becoming solid, the density is going to vary slightly. So if they're not fixed, they can drift away slowly. So in regular 3D printers that you use every day, if you want to write structures like this, you are usually required to print, a sacrificial material, a supporting structure. And after your printing is done, then you cut this off. So you cannot do that in TPP because everything is immersed in 2-photon resin. And if you want to print like this, the axial scanning is very slow, like a mechanical stage. So this is usually not allowed. So printing overhanging structures or complex or highly porous structure is a very time-consuming and challenging procedure. And these problems can be easily solved by the DMD system because we can write in any direction at the same speed. So without compromising resolution and speed. Okay. So the DMD system provides great flexibility and improves the writing speed for about 5 to 10 times. But we believe that is not enough because if you reduce the printing time of 2 months to 6 days, it's still way too long to print a small device. So we came up with another idea to further reduce the printing time, which is to use a pattern light sheet. So imagine a light sheet containing 1 million or several million points. If that's possible, then we can substantially improve the throughput. So, how was the idea realized and how did everything begin? So by looking at laser processing, in the past, laser is usually focused to a small point of focus through a lens, where at the focal point, it contains sufficient energy to process material. So we wonder if it's possible, instead of focusing to a point, we focus the light into a thin plane, okay? And this plane has a thickness of a micron or even thinner than a micron. And if this is possible, then can we generate arbitrary patterns on this plane? As a result, as we move the plane axially and at simultaneously varying patterns on the light sheet, we can realize fast 3D printing. Okay, so before I show you the method, I would again give you a quick review on femtosecond lasers. And we already mentioned that two-photon polymerization requires the use of femtosecond laser. And a femtosecond laser is a kind of pulse laser. Okay, so the intensity is not steady, it's a pulse. And the pulse width is on the scale of femtosecond laser, 100 femtosecond, which is a femtosecond laser. So you can also have pulse lasers on nanosecond or picosecond scale. So to have pulse laser, the main purpose is to maintain a reasonable or relatively low average power while substantially increase the peak power, peak laser power. So in this example, if you use a low repetition rate laser, let's say you have 1,000 pulses per second, and the laser is 4 watt. And if you do the math, you will find that individually each pulse contains, the peak power is 40 gigawatt. Just 10 zeros, a number that you can't imagine. And each pulse contains energy of 4 millijoule, okay? So that's a basic property of a pulse laser. But if you consider the Fourier transform of an impulse, it will give you an infinite spectrum, right? So for a typical laser of specific wavelength, the spectrum is very, very narrow, like a 0.1 or 0.01 nanometers. But when your pulse width in the time domain becomes very narrow, the Fourier transform is actually going to give it a relatively wide spectrum. So an 800 nanometer pulse laser, if you look at the spectrum, it can actually range from 760 to 840, very wide. In other words, it contains many colors. So the light sheet generation method is inspired by exploiting the wide spectrum characteristic of a femtosecond laser. So to achieve or generate a light sheet, a femtosecond laser is brought to a grating. So when laser sees grating, meaning one-dimensional periodic structures, the colors would disperse. In other words, going in different directions. Okay. And when dispersion occurs, the pulse is widened. Because total energy is conserved, the peak power is then lowered, and it cannot induce a multi-photon absorption or two-photon polymerization. And we then use an objective lens to recombine the dispersed spectrum such that they all overlap again at the focal plane. And after the focal plane, these different spectrums, diverge again. So as a result, there's only one plane in space where all the colors are merged together. And as a result, only at this plane, the pulse is narrow. And everywhere else, the pulses are widened. So this practically forms a light sheet because only at this plane, the laser will have effect to generate photopolymerization. So the generation of light sheet was not invented by our group. It was actually first introduced in 2005 by 2 groups simultaneously in the world. So this was first proposed and conceived for fluorescent imaging. As you can see, it only generates a light sheet, but not generating patterns on the light sheet. So this light sheet would be used to generate fluorescent excitation on a biological sample. Let's say there is a 3D semi-transparent biological specimen, and we shine the light laser to the specimen, and we only generate excitation on this very thin light sheet. And then the reflected light is then collected and imaged by an EMCCD camera. Okay, so this is called the temporal focusing multiphoton microscopy. So remember, in the past, this is done by laser scanning. So all the information at this plane needs to be acquired point by point. So now it's done in a single exposure. So the imaging speed is enhanced by several orders of magnitude. So essentially, it is equivalent to the laser repetition rate, and which is very often on the scale of megahertz. So the real imaging speed is actually limited by the speed of the camera, okay? Because now you can excite very fast, but the camera speed is not really matching. So the camera speed sets limit on temporal focusing microscopy, which is from a couple hundred hertz to, I think at most, a kilohertz. And in comparison to a point scanning system, which is just a video rate, is roughly 1 to 2 orders of magnitude enhancement. But if you use a light sheet to perform fabrication, you can do it much faster because photopolymerization can be done in a faster time scale. Okay, so this slide compares conventional spatial focusing versus temporal focusing, the idea I described. So in the past, laser is focused to a small spot to increase energy density for processing materials. And along the light path, the pulse width is a constant and doesn't change. In a temporal focusing system, you will notice that the spot is not narrow. Actually, you adjust the spot size such that at the focal region is equivalent to the processing area. So this can be, a couple hundred microns in diameter. Okay, but along the light path, what's changing is the pulse width, and it's only narrow at the focal point, as you can see on the left here. And only this plane, the peak power is sufficiently high to generate excitation or multiphoton absorption. This slide presents another perspective comparing spatial focusing versus temporal focusing. Okay, and as you can see, again, spatial focusing has a small focal point, pulse width remains constant. Temporal focusing, we're processing a beam, and only at the focal plane we have a thin light sheet generated. And the question is, how do we generate arbitrary patterns on this plane? So here is what we did. So we replaced the static diffraction grating with a digital micromirror device. And as you know, DMD has millions of mirrors, and each mirror has 2 states, 12 minus 12 degrees, right? So this is a DMD. So in a sense, DMD is a blaze grating, meaning, the profile is a sawtooth profile. A blaze grating has the characteristics of high power efficiency in specific orders. Okay, so if you place the DMD in the correct order, more than 50% of the laser power can be directed to the desired diffraction order for use. And when the laser sees the DMD, it again disperses, just like temporal focusing. But the DMD is also placed on a specific location such that it's in conjugation with the focal plane here. So basically whatever shown on the DMD is projected to the imaging plane here. And that also happens to be the plane where the light sheet is formed. So now whichever pattern we display on the DMD would be displayed or generated on the focal plane via the light sheet. So you can now compare the two systems. So in the first system, we use the DMD as a binary mask. And we don't really want the dispersion, and we try to compensate it. And in this design, we use it in a total opposite way. We use DMD and we use it to generate, we purposely generate dispersion. And the dispersion is only taken away at the focal plane. As a result, it forms light sheet for micromachining. So you can see here, we pattern the light sheet and move the light sheet on a nickel target, and it generates a very small feature. So if you study the feature size with the scale bar, you find that the minimum feature size is roughly 500 nanometers, which is roughly half the wavelength. So the light source has a central wavelength of 800 nanometers. So in other words, this is diffraction limited in terms of resolution. And for laser ablation or photopolymerization, if you fine control the laser power, you can achieve super resolution. So in order to do that over a large area, one key thing to address is to ensure this light sheet is going to be very uniform. And that is done by introducing this beam homogenizer. Okay, so your beam going out of the laser will have a Gaussian profile. So going through the beam homogenizer is going to be flattened to have a top flat profile. And if your laser has high enough energy, you would then only use, for example, center region of the beam. So to ensure it's just very, very flat and with uniform energy. So next, if you have a light sheet, what you can do easily is just to drill holes, right? So if this is a silicon substrate, we generate a light sheet and we move the stage and we drill holes. And as you can see, with extremely flat bottom and almost vertical side walls. And we probed the bottom surface with an atomic force microscope and found the flatness to be around 50 nanometers root mean square. On the left shows a simulated intensity profile in space. So what's interesting here is if we put the light sheet here, the light sheet contains extremely high laser energy. As I said, the peak power is on the gigawatt scale. So all material is going to be, I would say, eliminated, because this is not melting. This is also not sublimation. The energy is just too high. So if you look up in the literature, you will find ionic explosion or some fancy terms to describe what's happening here. Basically, the laser energy is too high that all the electrons are immediately ejected and the ions will explode and go out. So basically in air form. If you focus this laser in air, it's actually going to generate plasma in air. You will hear the hissing noises and see it glowing. So it's the level of power is quite insane. And now it's all constrained in a light sheet. So whichever the light sheet passes through, whichever material the light sheet touches upon, is going to be removed. And if we don't move the light sheet, although the laser is going down, it's not going to attack the material underneath the light sheet. So it's quite magical. So you're shining the light to a target, but it's not going to attack material underneath or before the light sheet. Okay. So this is a video showing laser micromachining process using femtosecond lasers. But this is not point scanning. This is done in a parallel fashion, and every laser pulses goes to the target. Some of the materials are removed. And as I said, this laser is at 1 kilohertz repetition rate. So 20 pulses means 20 milliseconds. So that's a very fast microfabrication speed comparing with point scanning procedures. Okay. Actually, let's take a break here. So if you have any questions, you can ask now, as this is a special research seminar related to two-photon polymerization. So if not, we would resume the lecture at 5:30. I'll see you guys in a little bit. All right, so let's continue on the topic on generating the light sheet for nanofabrication. So one implication of the light sheet generation for processing is that it may be compatible with some of the semiconductor processing. Because everything I just shown is only using a very low power level, 10 milliwatt to, at most, I think 30 milliwatt. And we showed that, over an area of about 100 micron by 100 micron square can be processed in just 10 milliseconds, 10 pulses with diffraction limited resolution. So, our laser has 4 watts. So in other words, if we scale up the processing area, we can, process 2 millimeter size area, same time and same resolution. And using a even higher powered femtosecond laser, we can process large area again at the same speed. So in a way, although this is not tens of nanometer resolution, this is a very good resolution and comparable with many of the semiconductor process. And due to the high power of the light sheet, it's not really picking on any material. It can process metals or even ceramics. So the only issue here is as we increase the large processing area, the DMD may not have enough pixels. Because in 100 micron size features, we're projecting every pixel to just 50 nanometer by 50 nanometer size. So everything is diffraction limited. Increasing size, each pixel would be projecting to a larger area. So if we still maintain on the fine line feature, we may be limited by this. But on the other hand, new DMDs are being developed on a yearly basis, and higher resolution units are produced at low cost. Okay, so once we have the light sheet, we then want to process photoresins. So processing opaque materials are different. Because the light sheet thickness doesn't matter. In the past, temporal focusing multiphoton microscope has an issue, which is the light sheet's thickness is thicker than the focal point axial direction. So usually a voxel, if you scan a Gaussian beam, is roughly 1.5 to 2 micron in size. But if you use the light sheet, the thickness is roughly 3 micron. So you are giving away axial resolution, and lateral resolution is the same. Okay. So by direct application of temporal focusing light sheet, we would increase the speed by 2 orders of magnitude, but giving away axial resolution. So that's not ideal. But we'll see how we address this problem in the next few slides. But we first want to demonstrate we can generate a light sheet, and as we scan axially, we can alter patterns to create arbitrary 3-dimensional structures. And on the right shows a very typical exposure time versus power characterization. So if you write with a low power, there is a writing threshold. So below which you will not see any photopolymerization effect. If the laser power is too high, then you will see boiling and bubbling in the photoresin. So within this window, between these two lines, is the processing area. Okay. And you can see you can write the same features. When your power increases, you're giving away some resolution. So once you identify the processing parameters, like processing area versus a specific laser power to get a certain resolution, we can start writing 3-dimensional structures. So in this example, each layer is defined in a single exposure. And then the light sheet is moved to a second layer, and so on. So every exposure for a single layer, and as I said, each exposure only takes 1 millisecond. Or, we can lower the laser total power and use 10 pulses to define a layer. So in a sense, let's say we define a layer with 10 pulses, we then can define 100 layers per second. And of course, what you see here is a video in slow motion, because if we print at a real speed, you would see nothing. In a blink of an eye, everything was done. And this is the written parts. So it's pretty much like acrylic, plastic, the printed structures. So it's semi-translucent. But if you bring it to the scanning electron microscope, you will see these log pile structures, largely hollow and very fine and high resolution. You can also see the artifact generated by a dead DMD pixel. Okay, so this is the printing direction. So each layer is defined in the XY plane, and then move to the next plane. Okay, so if we flip this pillar and we take an image in the XZ plane, we can see the axial resolution is also well preserved. Definitely comparable to the point-by-point scanning process. But this whole thing was done in just a few seconds versus the video I show you in the beginning of the slides. Printing that jet is quite a while. So next, how to fine-tune the resolution, or I should say, temporal focusing has a voxel of aspect ratio between 1:3 to 1:4. How can we make it round? I explained earlier that if the voxel is round, it will have better mechanical property. And also in the axial direction, we can write finer structures. So we develop a parametric model to see what's going on. And this parametric model includes all the optical properties, as well as the spectrum of the laser as one of the parameters. And here we simulate the written structure. So on the DMD, we display this grating pattern. And basically, we're writing these lines in space. And here is the cross-section profile. And again, in the simulation, we assume each DMD is mapped each DMD pixel is mapped to an area about 80 by 80 nanometers square. So it's super resolution. So in a sense, if you project the line using 1, 2, or even 5 pixels, it should give the same resolution, full width, half maximum. Why? Because it's super resolution. So if you use optics principles, it would give you the same size. What's different is intensity. So if you use only 1 pixel, then the light would be reflected to the processing field. So if you use 3 pixels, then intensity is 3 times. So you will see that below 3 pixels, no polymerization is achieved. And below 5 pixels, this is a line of diffraction threshold or diffraction limited size. And if you zoom into the diagram here, you actually see the intensity profile has a better aspect ratio than 1:4. It's actually better than 1:2. And here is how we did it. So conventionally, the spot size is only controlled by 2 parameters, right? There's lambda over NA and lambda over NA squared for lateral and axial resolution. But in a temporal focusing system, the axial resolution has another parameter to control, which is the spectrum, right? So the shorter the pulse width, the narrower the light sheet. So 3 parameters together determine the axial resolution of a temporal focusing system. The lateral resolution is still only determined by these 2 parameters. So here is what we did. We want the laser to have a broader spectrum, so we switched to a laser of even shorter pulse width, only 35 femtosecond. And next, if we remember what's happening in the optical configuration here. So the light is first dispersed and then recollected by the objective lens. So what we're doing here is we purposely clip off a portion of the spectrum. So when some colors are lost at the focal plane, the point spread function is going to be worsened. Okay. So we get wider spectrum here, but we purposely cut off some colors. So point spread function worsened. But we're very lucky to find that the lateral resolution is worsened at a higher speed than axial resolution. So by appropriately adjusting the color that we clip off, the spot size becomes round, and of course it becomes bigger. But bigger in size doesn't matter as long as we control the laser power threshold. We can write smaller spots. Remember the polymerization threshold is here. We can control the laser power to control the spot size. As long as the light sheet is uniform, we can then precisely reduce the spot size by controlling laser power. And we can achieve parallel writing with optimal voxel geometry. And here's a set of experiments running through different processing parameters using 3 pixels, 4 pixels to 6 pixels with different power levels. So 42 nanowatt per pixel as an example. And we find that minimum line width can be achieved through combination of these different processing parameters. And the best axial and lateral resolution achieved is 175 versus 140 nanometers. And the aspect ratio in the end we can achieve is around 1.2. So this is not only the fastest process, but also the process with the highest axial resolution. and the best voxel geometry reported so far. So this work is done in collaboration with Lawrence Livermore National Lab, where they provided custom designed photoresins suitable for femtosecond laser amplifiers. And we helped them with setting up the optics. So as you can see, finally, we achieved the best resolution reported so far. And the throughput is increased by almost a factor of 100 to 1,000. So commercial systems is writing at 0.1 cubic millimeter per hour. Okay. And we're doing 100. And because the laser costs so much and has a limited lifetime, if we can print 1,000 times faster within a given time, we are actually saving money. So per cubic millimeter, if we count the equipment and also manpower, it would cost only $1.50 US dollars per cubic millimeter structure with roughly 100 nanometer resolution. We also demonstrate how to write very large structures. As you can see, this is a bridge. So if you look at it cross-sectionally, on the side, it looked like something like this. So in the past, these type of structures cannot be printed by TPP. Because this is sort of a freestanding overhang structures, this is too big, and usually the TPP processing field is small. So once you print the structure and you want to extend to the right, you can't, because parts would be floating in the water and drift away. And we did this because things are done in such a short time. And before they can drift away, they are already connected and joined in space. And that's how this micro-scaled bridge was printed. So you can see the size is almost millimeter scale. And this result was published in Science in 2019. And here is a comparison with all the reported two-photon polymerization techniques. So on the top shows a lateral resolution, and the bottom shows axial resolution. The x-axis shows a printing rate, okay, in terms of cubic millimeter per hour. So you find that all the different methods is roughly moving along this line. So basically, everyone is trading rate with a resolution. So if you want to print very high resolution, then your speed is extremely slow. If you want to print fast, then you're giving away resolution. This is a spot on the scale of almost 5 to 10 microns versus 100 nanometers. So what we're doing, the DMD light sheet method is actually bringing everything to the corner. And laterally, we're not showing the best reported resolution, but axially, it's a 175. It's better than S4. And this is because the aspect ratio is tuned. So not only that axial resolution is a world record, but also the return mechanical structure will be more reliable and robust. Okay. So we also demonstrate the use of the light sheet in combination with electrode deposition to print three-dimensional arbitrarily designed metallic structures. So the process is done in a layer-by-layer fashion. So basically, if you can choose any 2 or 3 metals that can be selectively etched, you can use this method. So what you do first is on a substrate, you deposit a layer of sacrificial material or structural material. So you can start with either one. You then use a patent light sheet to perform parallel micromachining. After that, you deposit a second material. then you use the light sheet to flatten the entire structure. So just use a blank light sheet, it will flatten everything like this. And then you can repeat step 2 to step 4, and you can build arbitrary structures like this. And in the end, you etch away the sacrificial material, which forms a structure like this. So some people may wonder, how come this is fast? Because electrode deposition is slow. But on the other hand, electrode deposition is a scalable process. Because although it takes 10 minutes to plate a layer, but to plate an object of 1 millimeter in size is the same time as plating an object that's 1 meter in size. So for large-scale production, electrode deposition is definitely fast. And the light sheet is, defining patterns on millisecond time scale. So this actually enables large-scale, high-throughput production of 3D printing. And this one achieves a resolution around 800 nanometers. This is actually a work done before the TPP work, using the light sheet for demonstrating 3D printing. Okay, so this concludes the first set of slides. Mainly works in our team on two-photon polymerization using a multiple laser focus, as well as a pattern light sheet. Any questions? So if not, let's move on to the second special topic. So this set of slides is provided online, so it's shared in the Blackboard as a special topic PDF. And these materials is just for your information. It's a research seminar, so it's not going to be examined. And actually, I received a question from a student that the video link of October 7th is only just 5 seconds. And I apologize for that. I don't know what's happening to the Zoom online database, but I've sort of lost the video information from my Zoom account. All right, so let's move on to the next set of slides. So here I want to show you some work we have done on developing a precise roll-to-roll printing system to demonstrate micro contact printing or possibly other type of contact printing techniques that we have talked about in class, such as nano imprint. So our goal is to realize really large-scale continuous printing of flexible electronics. And the reason that we want to develop this system is there's a great variety of contact printing techniques developed in the past decade. And also in the meantime, a lot of high-impact publications, from top journals, Science or Nature. But after the publication, things were stopped. You see fancy demonstration on the scale of a millimeter in size, and showing things can be done in a roll-to-roll fashion, possibly, but you see none of them being realized. And our goal is to, really achieve roll-to-roll printing at large scale and achieving nanometer resolution. Okay. So why roll-to-roll? So roll-to-roll is well known for its high production speed and low cost. And if you imagine what's roll-to-roll printing, just imagine how newspapers are printed. It's done in a roll-to-roll fashion. So basically, you have a flexible substrate or web as shown on the left, and things just get printed as they roll. And a properly designed roll-to-roll system can print multi-layer devices at a speed of tens of meters per hour. And that is so much faster than semiconductor IC processes. So the main advantage is low cost and high throughput. And based on this reason, actually, this roll-to-roll process is the main driving force and motivation of flexible electronics. So when people talk about flexible electronics, they always claim low cost and roll-to-roll process. But the state of the art or the best roll-to-roll system you can find out there only gives you 10 micron to 100 micron printing resolution. So that's really not good enough for electronics. And as I explained, you really want that small feature and good alignment between the gate and source layers to achieve high switching speed and low power. And roll-to-roll process has been demonstrated in PV panels, photovoltaic cells, because the gate, the electrodes can be printed without high requirements on resolution. But electronics like transistors is a killer. It must have that resolution in order to achieve the desired function. So as I said, you can see PV cells being produced in a roll-to-roll fashion. So these are really low cost versus semiconductor-based PV cells. And they're also flexible and very versatile, can be easily installed and used in different places. So we talk about micro contact printing, in the earlier slides. So essentially, you start with a PDMS membrane, and you ink it with molecular ink, which is SAMs, or self-assembled monolayers, or thiols. So once that ink is properly dried, then you can transfer the ink to a metal layer like gold, and forming a SAM layer, and then followed by etching. So that's the basic procedure that we talk about. But there are two reasons micro contact printing was not adopted for roll-to-roll process. And similar for nano imprint, not exactly the same, but facing similar issues. So micro contact printing, the first issue is these formulations require long etching time because the same layers are very thin and the protection power is fragile. So it has to use very mild etching to etch. And the etching time is usually 20 minutes to half an hour. So how you cannot roll because you're rolling at tens of RPMs. It's sometimes very fast. So if you have to etch for 20 minutes, it violates the purpose or definition of roll-to-roll process. So new chemistries must be developed. So that's one aspect in terms of material processing. The second aspect is the feet of PDMS. We talk about PDMS feet better have a ratio around 1:1. So in other words, if we're printing 100 nanometer features, this foot would be 100 nanometers in height. And if we bring down the stamp in contact with the substrate, if we overpress by, let's say, 200 nanometers, then we will lose all the patterns. So for PDMS, extremely precise position control is needed to achieve a successful transfer over a large area. And that is very challenging. Okay. So in fact, nano imprint is easier to be implemented because the mold is a hard mold, okay? And it's printing on, for example, plastics using thermal forming. So overpressing is still going to result in reasonable patterns. Or UV epoxy is applied, and after rolling, you will still have features, unlike microcontact printing. So this is a example showing how nano imprint was demonstrated on a roll-to-roll setup. So you can see liquid resins is applied through the adductor blade and going through this region, and then UV exposure is applied, and you have a patterned structure on a flexible substrate. To address the precision requirement, actually various high precision roll-to-roll system has been developed and mostly use flexures to generate very precise motion guidance. And we would talk about flexures because it is also the main method used in designing MEMS or microscale devices. The reason is at microscale, you cannot design and fabricate multiple parts and assemble them. You cannot assemble microscale parts, and as a result, all micro devices are made in one part or monolithically. And this happens to be the most precise mechanical system to generate motions based on the compliance of the material as shown here. So the goal of this project here is to develop high resolution roll-to-roll printing process. And we did some calculation. We want to make sure during the contact process, the displacement must be controlled within 500 nanometers, and the force needs to be controlled within plus minus 0.05 Newton. Okay, and during printing, we must address the roller in multiple degrees of freedom, because it can be tilted or having arrows in different dimensions. For example, this is sort of exaggerated, but if you have two rollers bring into contact like this, then different areas, some areas will be overpressed, some areas will not have pattern transferred. Okay, so this is in Z position, but also rotation in different axes. So to print a single layer, 4 degrees of freedom must be addressed. For double layer printing, 5 degrees of freedom control of the roller position is required. So we first build a system to demonstrate a single layer printing. So the core part is 4 degrees of freedom flexure stage that precisely aligns and apply microcontact printing to moving web. So a roll-to-roll machine consists of actually quite some different parts. So there is the rewinding and unwinding modules. There is a tension control unit here where it actively monitors the tension applied in the web. And the web must be in tension condition and ideally around 0.1% strain to achieve a good printing results. As you have experience of scrolling paintings or papers, it will not scroll ideally. So scrolling means if you just scroll them and into a row, you will find that you will have tilt arrows, right? So to correct that arrow, we have a unit called web guide. So as the web moves forward, there is a edge finder. So there's infrared reading the edge position. If it's moving too far, then we have these 2 sets of parallel rollers that would rotate in the top plane. So this would generate a friction force to move the web in lateral direction for alignment. Okay. So this slide shows the design of the flexure stage. So this is actually very important, and I want you to pay attention to this because this mechanism is used very frequently in various MEMS devices, such as accelerometers, gyroscopes, or nano positioners. They all adopt these designs. So let's start with a single beam. So how do you generate guided motion? Let's say this is your object here. So if you use a flexible beam, which is essentially a thin beam, you can then move it, right? It has 1 degree of freedom. But as you move, you will find it's actually not moving along a straight line, right? Because it's tilt. So it's generating axial translational arrows and angular arrows. So what you do is you use 2 beams and connect them to a stage. So this will be a better design. So as it moves, it removes the angular arrow, but translationally it still has some arrow. If your displacement is large, then the stage can move inward because you have to use your imaginary to see these arrows. So then people came up with a configuration of flexing beams. This is called double parallelogram mechanism. So here is the ground, and you have 2 flexing beams and connecting to a stage. So this is actually called the secondary stage. And on the secondary stage, you use another 2 beams to connect to the main moving stage. Okay. So as the main moving stage moves, the secondary stage will move half the displacement. So for large displacement, these will move inward, right? Like I mentioned. So this would move inward, but the main stage would not move laterally. Okay. And this also allows large displacement. So some people would be like, if I want to move the stage, why can I use this design? Okay, so if I have 2 beams here, and I put another 2 beams here, so I can push it, and the lateral arrows will be removed because now the device is symmetrical, right? But the issue is if you move for large distance, and these beams will be like this. Okay, and I don't know whether you notice this or not. This beam is now elongated. As the stage moves forward, these beams will be bent and pulled axially. So this is not going to happen because the axial stiffness of a beam is roughly 1,000 times higher than the bending stiffness. So essentially, you are not able to push. You will quickly, if you force push it, it will quickly yield the beam and damage it. It would flex for a long distance, but axially is quite constrained. So this double parallelogram mechanism also relieves this issue. You can move a long distance when the beam is trying to be pulled axially. The secondary stage relieves the motion. So the secondary stage actually moves in, and all the beam length is not influenced. So we can flex for a long distance. So that's a double parallelogram mechanism, and we can make it symmetric. So that's a 1 stage in the center that moves the roller up and down. Okay. And here is another 4, which is also symmetric. So this one generates the motion laterally. So the top 2 make it symmetrical to double the strength. So that's how it works. So you can see the animations here to see how the flexures move. So this one is generating lateral motion in the X direction. and this one is moving in the Y direction. And again, please try to understand how these things work, because this is essentially the same design principle that we frequently use in the second part of the class when we design MEMS devices. So this will be easily MEMS devices, a 2D stage, monolithically made. Okay. So based on mechanics of materials, we can easily estimate the stiffness in different directions. So X and Y and theta Z, torsional stiffness. Okay, so if we combine two monolithic stage, we can, so each stage have X and Y, so together, so they can also move in Y and X, but they can also rotate about Y, right? So this one moves forward, the other one moves backward, then it's rotating about the Y axis. And can also rotate about the X axis. So 4 degrees of freedom. So to ensure high precision, air bushings or air bearings are used to support the roller. And we drive the compliant mechanism using a solenoid actuator. So here is how it works. And we use a capacitance probe to measure the displacement. So capacitance probe is one of the most precise non-contact sensors. It usually have a resolution of 50 to 100 nanometers and with a sampling rate of 15 kilohertz. So this will be sufficiently fast and high resolution for closed loop control. So then we model the dynamic system. So basically F equals to MA, but then we have multiple systems. The 2 degrees of freedom system. If we are looking at the roller as an object and 2 supports. Okay, so we can decouple the other direction, which is moving out of the plane. This will simplify the model and it's reasonable. Okay. So so this is basically in the roller moving in the Y direction. The roller can also be moving in the X direction, but that is decoupled. And we do this because a Y direction is ensuring the uniformity. The X direction, once it's calibrated, it's sort of fixed. And Y direction, during all printing time, it should be actively controlled. So we model, there are 2 ways to describe this being. There's Y1 and Y2, 2 coordinate system, or we can describe the center position and plus a rotational degrees of freedom to describe the roller. And that's what we use. There's Y and theta forming a second order dynamic model of the system. Okay. So if you're not familiar with dynamics and mechanics of materials, don't worry about it. We're not going to require you to repeat the derivation process. But essentially, we're relating the output displacement to the driving current through the second order dynamic equation. So basically, we apply Laplace transform and find the transfer function G11, G12, and G22. And ideally, if the 2 channels are decoupled, meaning if we can independently control Y and theta, then these 2 should be 0, right? But apparently they're not 0 and quite complex. So we will show you how this can be addressed in feed-forward control. Before we apply control, we characterize the basic mechanical property like natural frequency of the system, damping ratio, This is found through an impulse test. To ensure good flexing range, we use a material of aluminum 7075. Okay, and as I said, flexures are the mechanism that has the highest repeatability. It will have arrows in terms of positioning, but these arrows are repeatable. So the arrow sources are from fabrication arrows. So, we can measure these parasitic arrows and apply them in the control system to eliminate these arrows, which are within hundreds of nanometers range. And this slide shows the feed-forward control diagram for the roll-to-roll system, just considering the y-axis. Okay, so this is a feed-forward controller. So this is the plan to control P11, P22, and P12. So D is the feed-forward controller, and C11 and C22 are just regular a controller. So we use actually two signals. There's the position signal from the capacitance probe. I forgot to mention that in the stage, we are also integrating a load cell to measure the printing force in situ. So on the control diagram, we also have force input. So there's signal from the capacitance probes, and there's signals from the load cells to complete the loop. And here we show the modeled dynamic curve versus the measured. And you can see they match quite well. So the model is from the dynamic equation that we show in the last few slides. Okay. So this slide shows the feed-forward controller's load cell position. So it's basically integrated with the print roller. So the impression roller is integrated in the impression roller. So during printing, impression roller is bring down to a very close position. And the print roller is loaded with the PDMS stamp. And the voice coil actuator will then precisely control the position to ensure parallel contact, and load cell monitors the printing force. Okay. So I think we're running out of time. Let's actually stop here. On Wednesday, I'm going to finish this seminar on roll-to-roll printing of micro-contact printing. Okay, so if you have any questions, feel free to send me an email. So I will see you on Wednesday.